Good afternoon, everybody. We welcome Professor Stephane Goriely today from Institute of Astronomy and Astrophysics in Brussels. Those who don't know him, he has been in forefront of making mass models for the whole nuclear chart for a couple of decades now. And he has also been one of the leading researchers in finding different aspects of nucleosynthesis and its different problems theoretically. And this is exactly what he is going to let us know today, the modern problem. And so Professor Goriely, please go ahead. And I ask all the listeners to keep themselves muted unless they need to speak. And unless you have no pressing questions, please keep your questions for the discussion to finish. And then if you want to put your question on the chat, feel free to welcome. So Professor Goriely.
Thank you very much. So thank you to all of you to be here. Good morning, good afternoon, good evening, depending on where you are. I will talk today about some open questions and some probably controversial and speculative issues related to the nucleosynthesis of the elements heavier than iron, so the so-called heavy elements. I will start mainly to discuss about issues that you are probably all aware of, but just to raise a few open questions and to put a bit the stage for other type of nucleosynthesis processes. So as you all know, I mean, you know, the elements heavier than iron are typically making about 2/3 of the stable nuclei, although they represent no more than typically 10 to the -6 in mass of the total available work. Okay, cannot. Well, I will try this way. Not more than 10 to the -6 in mass. So we are talking about these elements here, which we know in the solar system relatively well, and they represent a relatively small amount again of nuclei. So we also know from the start that these nuclei cannot be produced really by charged particle captures, like all the elements lighter than iron, simply because the timescales for capturing protons and alpha particles in a typical thermodynamic environment, thermonuclear environment, will take time which are typically much larger than the evolution lifetime of a star. And this is why already more than 60 years ago, the concept of neutron captures was brought in, which of course helped to avoid the problem of Coulomb barrier. For neutrons, as you know, there is no Coulomb barrier. And also quite naturally explain the peaks that we observed in the solar system at the neutron magic closed shell, typically at n = 50, n = 82, and n = 126. So from the start, and for a long time now, we know that most of the nuclei above iron are produced by neutron captures. And indeed, we have this so-called S-process nucleosynthesis, which is supposed to explain about half of the elements heavier than iron, which works relatively well, in which we believe that the neutron capture is relatively slow compared with the beta decays, in such a way that when you capture neutrons, for example, starting from iron nuclei, you will actually produce nuclei that are rapidly beta unstable and that will decay back to the value of stability. So this process is believed to take place on timescales of the order of years, 10 years to about 1,000 years, with neutron densities which are of the order of 10 to the 8th neutron per cubic centimeters, and it's essentially a competition between N gamma and beta decays. So for the last 40, 50 years, we know that the S process takes place in the core helium burning of massive stars, and also quite importantly in the low mass AGB stars during the so-called third dredge-up phases. There are, however, a number of questions that are still important and that should not be underestimated to try to better understand the S process. And one of the major questions is really how the neutrons are produced, especially in AGB stars. Although we have ways to produce neutrons, I would say quite artificially, the role of the various mixing mechanisms, meaning the overshoot, the rotation, and so on, is still far from being under control. So really how much neutrons can be produced in these stars and how they a production of neutrons can vary, particularly with the mass of the AGB star or the metallicity, the initial content of the star. It's really still an open, I think, open to research and still needs more effort. The contribution of also intermediate mass AGB stars, so stars typically from 4 to about 8, 9 solar masses, so these super AGB stars, including also super AGBs, are also open to questions on how much they can contribute actually to the S process nucleosynthesis. There is also a number of specific observations that are difficult to explain. A lot of them can be quite well explained, but some of them, like the one you can see here, where you can see actually post-AGB observations where the different elements like barium and zirconium have been obtained from the so-called heavy or light S elements. As you can see here, as a function of the so-called metallicity, so the amount of ion inside the star, and whatever they are, you can see that the models will predict something which is quite far from all the possibility that nature seems to show to us in these post-AGB stars, which are enriched with S-process elements. This type of observation, where models are still far from explaining the variety of S-process in these stars, is still open to question. And this is not the only one. We also have stars which are carbon poor and S-process rich. We can hardly understand. There's also the issue of the lead stars in the lead content in low metallicity stars, which shows much larger variation than what we observed. So all in all, I would say that the S-process is not badly known, but there's still open questions. And on the nuclear physics side, of course, we are still led to the uncertain neutron capture cross sections and temperature dependent beta decay rates of the unstable nuclei that are produced along the S process path. So this is for the S process. It's a subject that has been quite widely discussed and will still be discussed, I guess, in these seminars. Now we also have the R process. So the R process, as you know, is the headache of nucleosynthesis. It's probably the most complex and complicated process, where we have, in this case, neutron irradiation that is such that the typical time scale for neutron capture are by far smaller than the beta decay rates. We had, in this case, driven inside the valley of the neutron-rich region, where exotic neutron-rich nuclei are produced far away from the valley of stability, where the S process used to or can be expected to take place. This R process nucleosynthesis is believed to take place on timescales of the order of seconds, with neutron densities that can reach 10 to the 24th, but also up to 10 to the 34th neutrons per cubic centimeters. So it's, in this case, a kind of competition between neutron captures, photoneutron emission, beta decays, and fission as soon as the most exotic nuclei are produced. And it's believed to take place, of course, with such timescales in explosive conditions. And one of the major questions is really, and still remain, what is the R process site, which is now today probably still a competition or possibilities due to supernova explosions or neutron star mergers. And as you know, some of you might know, this is one of the top 11 questions that has been raised by the physics and astronomy departments of the national academies, where it's still an open question, despite the fact that we have observed, as you all know, a kilonova a few years ago, and that we still believe today that it could be a potential dominant site for the R process. It doesn't mean that other sites are not contributing. In particular, there are clear signatures that we need indeed very high neutron capture, very high neutron densities, that it will be in an explosive environment, and that the galaxy has been highly enriched already early in the life of the galaxy, but still a number of open questions on the R process remains. What is the dominant site of the R process? Are we talking about neutron star mergers only? Should we also get some contribution from magneto-rotational supernova explosions? Maybe. Are the collapsars, these rapidly rotating remnant that are coming out of some supernovae, are they also contributing or not, or are there other type of sites that could also contribute to their process? And for each of these sites, the frequency and the properties are, of course, needed. And to what extent do we actually have this under control? In particular, how well are we capable of describing the mass and the velocity of the ejecta, the coalescence time for the binary systems, and so on. In many of these sites, we also have problems related to neutrino transport and neutrino interactions, which could impact the neutron richness, especially during the neutron star merger dynamical ejecta, but also during the collapsar ejecta. We also have issues related to the exact angular and velocity distribution of the ejecta. And also when we deal with observation, there are observations that are still remain very difficult to explain, in particular the enrichment in very old so-called ultra-meta-poor stars, which for some of people are universal, but in fact they are not as universal as often claimed. We also have issues in ultra-faint dwarf galaxies that is telling us and a few things, and that we are trying to better understand. And at the end of the day, of course, the chemical evolution of the galaxy will have to be better understood. Now, on the nuclear physics side, it's not a surprise. Many of you are working in this field. So the nuclear physics part, we need reaction rates, including, of course, nuclear masses, but also beta decay rates, fission rates, and the fragment distribution, as well as the description of the equation of states of dense and hot matter, if we want to describe these difficult sites in which the R process is believed to take place. So all these questions are still pending. There are many of you that are working on that, and I will not elaborate many more on this at this stage. Some of you might also be aware that there's been quite some discussions lately on the intermediate so-called I process nucleosynthesis, which would be an intermediate process between the S process and the R process. So with neutron densities which are now of the order of 10 to the 13th up to 10 to the 15th neutrons per cubic centimeters. It's again a neutron capture and beta decay competitions, and different sites have been proposed, in particular the low metallicity AGB stars or the rapidly accreting white dwarfs. I would not extend myself on this topic because I know that in about a month's time, Arthur Chopin will discuss mainly on this topic, and which is quite an interesting topic, which still raises the problem of the contribution of the I process to the galaxy enrichment, and in particular to our solar system, which is still an open question. Finally, as you all know, there is the P process, and the P process is the process that is needed to explain the elements that are on the left side of the valley of stability, and that cannot be produced by the neutron captures, because as you can imagine, the neutron capture always bring you on the right side of the valley of stability by the radiative neutron captures, and therefore will bypass the possible productions of these P nuclei, the about 35 nuclei that are on the left side of the valley of stability, and that can obviously not be produced by neutron capture processes. So for this, we need a specific process, which is often called the P process, which produces the P nuclei on the left side of the valley of stability, mainly by different mechanisms like the photodisintegration of already produced S and R nuclei, which will then be photodisintegrated by gamma N, gamma P, and gamma alpha reactions, and bring this flow on the left side of the valley of stability to produce these P nuclei. And this process is also believed to take place on timescales of the order of a second, and on with temperature typically between 2 and 3 billion degrees, not less, not more. Otherwise, you would either not produce or these P nuclei, or you would destroy them. And this is through these photodisintegration reactions, and this is expected to take place in particular in type 2 supernovae, in particular in the oxygen neon layers during the explosion, or potentially in the interface between the proto-neutron star and the ejecta through this so-called neutrino P wind, which still also has been proposed. We also believe that the type 1a supernova could potentially produce the P nuclei quite efficiently, but it's a few questions, of course, remains. And one of these questions on the P process is indeed, what is the contribution of type 1a or proton-rich neutrino-driven wind, if any? That's one open question, of course. And one of the most difficult one, which has probably not been tackled enough in the past, is what really are the seed nuclei feeding the P process, especially in the binary system, in the type 1a supernova. It remains quite problematic to describe properly the possibility to produce heavy nuclei by S process, for example, before the P process takes place. An open question remains the origin of molybdenum 92 and 94, as well as ruthenium 96 and potentially lanthanum 138, though there are some proposals for this case. But for the molybdenum and ruthenium, quite systematically, we keep on underproducing here, as you can see here in a kind of typical plot in P process nuclei during the explosion of type 2 or type 1a supernova. As a function of A, you will get actually an underproduction with respect to what we have in our solar system systematically for molybdenum and ruthenium, while all the other P nuclei can be quite well explained through these explosional mechanisms at this temperature of 2 to 3 billion degrees. Another question which is also of interest is the role of neutrinos for the synthesis of quite some rare species like lanthanum 138 or tantalum 180, which remain quite difficult to ascertain at some point. And on the nucleophysics side, indeed, we will need to describe all the photodissociation rates for the thousands of nuclei involved, which is, of course, an open challenge, especially that these nuclei are usually not available experimentally or difficult to produce. So all in all, we know these various nucleosynthesis processes, and most of you know them. So there's no anything new here. We know that to produce the light nuclei, we will need the Big Bang, the hydrostatic or explosive stellar burning phases in the different stars of different initial mass or metallicity. Lithium, barium, and boron will be obtained by spallation on galactic cosmic rays. But for the heavier nuclei here, we will call for the S process, the I process, the R process, or the P process, as I just explained to you. It works relatively well, and all these processes are based on thermal nucleosynthesis, which are obtained in a given astrophysical plasma, heated at a given temperature, at a given density, except for the lithium, barium, and boron, for which a non-thermal nucleosynthesis is called by galactic cosmic rays. And I'll come back to it. And of course, we know the solar system abundances and the way the abundances could be obtained by almost all these processes. And as I try to show to you, there are quite still many open questions that are needing quite intense research for the years to come. Of course, the nucleophysics is far from being under control neither. And you have here a very small, rapid sketch of the heavy task that nuclear astrophysics has to answer to, mainly all the nuclear reaction being charged particle reactions for the Big Bang or the hydrogen to silicon burning phases, hydrostatic or explosive, as well as the different S, P, I, or R processes for which hundreds or thousands of nuclei have to be known, and all their strong electromagnetic or weak interactions have to be estimated either experimentally, always better, or theoretically, if not available, experimentally. So this raise a lot of questions still regarding the associated nuclear physics input, and many of you are working on that. So all what I've been saying now today is probably something which is not new to you, and I'm pretty sure that you are all working very hard on trying to help solving all these issues, which are still remain extremely important because they really represent the origins of the elements in the universe. But I would like, maybe now that I have the opportunity to give this seminar, to discuss an issue which is probably more controversial or more speculative, and which is a number of observations that remain puzzling and can hardly be explained actually by the standard thermal nucleosynthesis processes. So these processes that take place through thermonuclear reaction in an astrophysical plasma. And to do that, I would like to show you a few cases where actually, there's been a lot of work, especially on the observational side, and maybe a lack of explanation that could actually go in that direction, or even more interesting, maybe a new kind of field in which there will be interest for nuclear astrophysicists, both from the nuclear physics and the astrophysics modeling sides. So to show you a bit the situation, I took this extreme case of this star, which is called HD 101065, which is also known as Przybylski star. It's a difficult name to pronounce, so I'm sorry if I don't do it properly. But has been discovered in 1961 by the Australian Polish astronomer Przybylski, which is a very unusual star. It's a so-called ρAP star. So it stands for rapidly oscillating A-type star with a chemically peculiar, P stands for peculiar abundances. It's a star which has a very strong magnetic field and for which the spectroscopy has been done for about 57 elements. So after the Sun, it's probably one of the stars which has been the most studied. But it's an extremely difficult atmosphere to study observationally and to deduce, to get the abundances out of it, essentially because it's dominated by rare earth elements. There is an absence of ion group lines, there is line blanketing, and the atmosphere is very abnormal and highly stratified, leading to non-LTE effects and difficulties linked to the modeling of the atmosphere. So this star has been shown to be one of having a very specific, difficult, abnormal atmosphere and abundances. It's part of the so-called chemically peculiar stars, so the CP stars, which are classification of stars which show very abnormal abundances in their their surface. And you can see here in a logarithmic scale as a function of the element Z, you can see that you have the observation of these HD 101065, so this Przybylski star in the solid dots, compared with the one that you have in the Sun, which is shown by these open circles here. And as you can see, this star is quite abnormal in some in different respects. It has a very relatively low underabundance of carbon, oxygen, magnesium, or calcium. It has an overabundance of lithium with respect to the Sun by 2 decks, so about 100 times more lithium in this star than you have in the Sun. The ratio of lithium-6 to lithium-7 is also about 4 times bigger than what you have in the Sun, as you can see here with a ratio of 0.3. This star is also characterized with a cobalt to iron, which is about a factor of 0.4. So as you can see here, about 100 times larger than what you have in the Sun. And also, as you can see here directly, this is a logarithmic scale, you will see that you have in this star about 3 to 4 decks higher, so about a factor of 1,000 to about 10,000 more heavy nuclei that you have in the Sun. And as you can see here, also you have thorium and uranium, which are also quite abundant. And this star has been extremely widely studied, especially by the group of Professor Goriely in the years of 2000 to 2005, 2010. And it's clear that this star is quite exceptional. It's an extreme so-called AP star, but it shows quite similar features have been also observed in other so-called AM or AP stars, but also in BM and BP stars. So these stars which are of A-type or B-type, which are either rich in metals or peculiar in their abundances. And since there's been observed in these stars, which represent a significant proportion of A-type stars, in such a way that actually these peculiar stars, so-called chemically peculiar stars, are actually in the majority on the upper mean sequence. That led Coates in 1992 to say that these peculiar stars are actually normal. So there are many, these are not exceptional stars. And one of these other type of stars are the so-called Mercury-manganese star, like Goriely, which is now shown here in a logarithmic scale as a function of z, of the charge number. As you can see here, the sun is shown in from the Lotus abundances, elemental abundances are shown with the black dots, while we have Goriely shown here as a red squares. And this is the difference between the red squares and the circles here on the right side, that you can see that you have differences that are not so important for the light nuclei, but as soon as you go to the heavy nuclei, you can see that you have, in particular in the region of mercury, platinum, gold, thallium, you have an overproduction or an overabundance of these elements by about 5x. That means about a factor of 100,000 more than what you have in the sun for these particular abundances. So these stars, and these are not exceptional stars, are quite peculiar in the sense of their abundances. So how did we actually explain these stars? And these stars have been explained for the last 50 years quite systematically through the so-called radiative diffusion processes, which were introduced by Michaud in 1970, which tells you that actually light absorbers elements which are sensitive to the absorption of photons will be pushed up to the surface, while the others, which do not absorb light, will actually sink under gravity and settle down lower in the star, in the envelope of the star. And this theory has been quite successful to explain most of these, at least qualitatively, these stars, which they're very peculiar atmosphere and peculiar abundances which have been determined. Now there are some puzzling observations also claimed that were followed. And some of this claim came actually for these two stars, in particular, Przybylski star, but also another, its so-called twin star, HD 965. And again, in the years of 2004 to about 2006, there's been claimed that actually at the surface of the star, technetium, which, as you know, has a half-life at a maximum of 4.2 million years, but also promethium. So promethium is an element Z equal 61, for which there is no stable isotope, and for which the fastest decay is has a half-life of about 18 years. So this was an observation that was done at the surface of these two stars, which called for, of course, very open new questions. Is that how can you get technetium? Okay, technetium, we know we can make it by this process, blah, 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 but these stars are not necessarily binary stars. And where is this technetium could come from? Where is this promethium with a half-life of 18 years potentially coming from? This is one thing. The other thing is that there's been also claim that about the identification of about quite a huge bunch of lines, 436 lines, as you can see, for elements between polonium, Z equal 84, up to 99, so Einsteinium. All these subactinides or transuranium nuclei between, so again, 84 and 99, have been, some of them, so a lot of them have been identified, and quite a few lines, as you can see here, for example, for polonium, which has a half-life at the most of 102 years. About 35 out of 45 lines known have been identified, and so on, up to even Einsteinium, where with Z equal 99, with a half-life maximum of 1.3 years, for which about 39 out of 71 lines have been plausibly identified so meaning that these elements should be present somehow inside this surface of the star. And obviously, in this case, diffusion can hardly explain such observation. Diffusion can take some of the elements up and down, but they cannot modify, produce exotic, unstable nuclei like promethium or this trans-uranium. Now, I clearly put here if confirmed, because as you can imagine, these are extremely complex observations, and we have to be careful because these such claims were also done in 1972 by Jacek and Brandy in the specific star, where an AP star again was with a weak magnetic field was claimed to be polluted by lines of americium and curium, also is equal 96 and 95 and 96, also with short half-lives and with different lines. No promethium was detected, but however, a few years after, it was shown by Adelman and Piper that actually these are not transuranium, but rather lines of high excitation excited states of neutral and single ionized iron peak elements like chromium and iron, which were not studied at that time in the laboratory and which actually are are actually present in the atmosphere, but not americium and curium. Now, what to believe now? I think it's interesting to see that the work that has been done by Goriely and co-workers in the years 2000 still is raising quite an important problem about the presence of promethium, again with a half-life of no more than 18 years, can still be present in these two stars. And to quote Goriely and co-workers is that the spectroscopic evidence is strong enough that we would declare promethium to be present without hesitation if any of its isotopes were stable. So as we know, they are not stable. And so people are questioning, of course, themselves about the presence of promethium in the star, but there are quite a few works, at least during this year, that were pointing out this possibility of promethium to be present. And clearly, if confirmed, this would be impossible to reconcile with the diffusion theory. Now, in the Goriely star that I just showed you, which, as you can see again here, which differs quite significantly from the solar abundances, which you can see that again, that these abundances in Goriely for the different elements, especially in the manganese, in the mercury region, is about a factor of 100,000 larger than what you have in the sun. And still, there is also another observation that some of these mercury manganese stars, which are a real class of chemically peculiar stars of B type, actually platinum, mercury, and thallium were shown to exist almost entirely in the form of their heaviest isotopes. So in Goriely, for example, it was shown that platinum 196 and 198 were present, but platinum 194 and 195 were absent through a study of the isotopic shifts. And it was also claimed that mercury was essentially in the form of mercury 204. Again, here, it's quite difficult to reconcile with the diffusion theory. So all in all, there are some questions about these stars. And when looking at these stars, it's clear that normal thermal nucleosynthesis processes can hardly explain why these stars, unevolved stars, giants, dwarfs, are polluted by unstable radioactive elements. And so one of the possibilities that was already raised in the 60s through Cameron, Brancazio, Fowler, and others were actually to ask the question, are actually nuclear reactions possible? Can they possibly explain such observations? Of course, the question of the chemically peculiar star are quite important because can we trust fully the spectroscopic observation, knowing that the atmosphere are extremely complex, abnormal, stratified, non-local thermodynamic equilibrium being present? But still, what are the origins of the anomalies? Are they due to diffusion, to accretion, to magnetic activities, and possibly to nuclear reaction processes? Are the global are the impact on the chemical evolution? Are the global evolution of the galaxy also affected by this type of processes, or not at all? And these are questions that have not been raised and are not for which you can hardly see many work in the literature or around the world at the moment. So one of the questions I want to raise here is actually to what extent can these stars, be explained by nuclear reactions taking place at the stellar surface, or maybe outside through the interaction of this type stellar energetic particles, so accelerated protons and alpha that in a way or another, either from magnetic fields or from cosmic rays or from jets, and how this thermal nucleosynthesis, non-thermal nucleosynthesis could actually provide some answers. So we know that the non-thermal nucleosynthesis is quite important in different respects, and I told you already that the LiBeP, so the lithium, beryllium, and boron in the universe is actually believed to be coming from non-thermal nucleosynthesis, essentially from spallation reactions of accelerated carbon, nitrogen, and oxygen, accelerated at high energies that will interact with the protons in the interstellar medium. And this interaction of accelerated carbon, for example, with protons, will lead to a number of spallation reactions that will produce boron, beryllium, and lithium in the quantities that we believed are the one we see today in our interstellar medium and in all around our galaxies. Now, these non-thermal nucleosynthesis processes are also believed to be at the origin of relatively short-lived radionuclides, such as beryllium-7 or 10, aluminum-26, calcium-41, manganese-53, niobium-92, that we know that have been alive in meteorites and lunar rocks early in the solar system. And to explain these radioactive nuclide, short-lived, we actually called again for the jets and accelerated particles that must have taken place during the first phase of the formation of the solar system. Now, the question is, to what extent can we use also non-thermal nucleosynthesis to explain at least some of these chemically peculiar stars, or also maybe produce other elements heavier than iron more globally? And we know that we have quite a lot of places where protons and alphas are accelerated. And these are, for example, stellar flares, and in particular the solar flares at the surface of stars corresponds to protons accelerated at quite high energies with fluencies, that means the number of particles per unit centimeter, per square centimeters of about 10 to the 17th to 10 to the 18th protons per square centimeters. But this quantity here, that means the number of neutrons that are actually accelerated, could be highly enhanced, especially in young stellar objects like the one we have in our sun at the beginning, or also in the binary companion through the accretion disk. And we believe that the proton fluencies that are needed to explain this radionuclide at the early solar system phases is about 10 to the 23rd particle per centimeter square. We also know that in the case of protons, if they are guided along magnetic fields, these fluencies, so the number of particles per unit square, per unit surface, could actually be increased almost by a factor of 1,000,000. We also have jets, of course, in supernova explosions, bipolar ones, where we can estimate also the number of particles per second to be about 10 to the 37th particle per cubic centimeter per centimeter square per second at a radius of about 1,000 kilometers, and of course with velocities which are of relativistic velocities, which corresponds to energies of about 10 MeV. So we have these jets all around the galaxy, or around the universe, and how could they contribute in a way or another to this nucleosynthesis, or at least to some nuclear reactions? So we made up a simple, I would say, very simple non-thermal nucleosynthesis model to try to study that, which corresponds simply, I would say, to some initial material, like having a solar composition made, for example, also or differently of CNO elements or only carbon, which would be irradiated by accelerated protons and alpha particles with a given amplitude of their flux and a ratio between protons and alphas. They will irradiate this material during a given time of milliseconds, or could be seconds, hours, years, hundreds of years. This material, these projectiles will have a given energy distribution that could be either constant between in an energy interval, or like galactic cosmic rays follow a power law which is usually taken with a decreasing energy as a function of power law with an exponent of 2 to about 4. Interestingly, also, when you have such environment, these protons and alpha with emit neutrons that can then be thermalized on a given time scales that could usually be smaller than the irradiation times. In that case, you would produce neutrons that can be recaptured. And of course, in this type of models, you can superpose different type of events or mix the affected material, the nuclearly processed material with unaffected stellar material. At this stage here, there is no will to try to get more insight from the astrophysical side in the sense of having a realistic model for the production of these accelerated particles like MHD. That would be quite logical. And only a purely parametric approach is followed, like the one we had for the S process and the R process about 50 and 40 years ago, when we studied these processes simply by a canonical model at which the neutron irradiation was done at a constant temperature and constant density for a given irradiation time. So it's a bit the same philosophy. And in the same philosophy, you basically have to solve a simple, more or less, reaction network, which will include all the species that you want. Here in this case, about 5,600 species linked by many more reactions, because now at high energies, you might produce a number of, as ejectile, a given number of neutrons, protons, and alpha particles. So they are linked typically by 142,000 captured reactions, and including all these reactions into a reaction network, you can then try to find out the possibility to produce in a way or another the different, or to see how this material is processed by these accelerated particles. And of course, you need to know all the effective protons and alpha capture reaction cross-section, which at this stage is not anymore a reaction rate, but really a reaction cross-sections for energies that could go up to a few hundred MeV if you assume so. And of course, you need to have the partial effective cross-sections also. So just to give you a bit of a sense of what's going on is, if you take some solar type material that you bombard by a flux of accelerated protons and alphas up to an energy of 10 MeV per nucleon with a given amplitude, a given ratio of alpha to protons, and a given time of irradiation, you will see that the material that you have here, which is initially the solar initial material in red as a function of the elemental abundances, here the abundances as a function in a logarithmic scale, you will see that after 100 seconds, you will not have affected much, but you will have somehow processed part of the material and shifted it a bit to higher masses due to the capture of protons and alpha particles. Now, if you irradiate a bit longer than 100 seconds for this type of flux, you will get more heavier and heavier nuclei that, as you can see here, after 1,000 seconds, will start to produce significantly the heavy elements. And just for comparison, I showed you here the black dots, which correspond to this Przybylski star, HD 101065. And you can see that you start to produce more even than what you have in the star, just by capturing protons and alphas on this solar-like material. Now, if you go up to 1,000 seconds, this is what you get. It's a huge fluence. So you have a flux of about 10 to the 27th particle per cubic per square centimeters. And as you can, during about the 10,000 seconds, and you can see that you have now produced even nuclei up to the actinide region. Now, if you do the same, but you include the capture of thermalized neutrons, you see that actually you are producing now, you start to have a kind of structure, which is more linked to the capture of neutrons in this specific environment. And then you can play with that and mix it with unaffected material. If you assume now that this material that you initially have is mixed with material that has been processed by this spallation reaction, you can see that you get, with a given mixing of 98% of solar initial abundances and 2% that has been nuclearly processed by these stellar energetic particles, you get something in between, which is this green curve here, which can now be compared with what you have in Przybylski star. And as you can see, okay, it's not perfect, but you have a way through nuclear reactions actually to even produce these heavy nuclei, including a lot of lithium-6 to lithium-7. As you can see here, you produce something which is very close to what you have in the star as observed. You also could explain the cobalt-2 ion, and potentially also, of course, in this type of environment, you will have no problem to produce technetium, promethium, and even actinides, as you can see here, that are produced in this environment. So now, before closing on this topic, but I will just also mention to you this so-called mystery of phosphorus-rich stars that have been discovered about last year by Thomas Masseron and his colleagues, and which has been published in Nature last year, which is very interesting observation of quite some stars, 15 phosphorus-rich stars, which have all the properties of having a metallicity of the order of -1 in iron to hydrogen. So that means a content of the stars have a content of iron about 10 times less than what you have in the sun. And you can see that this overproductions of phosphorus with respect to iron is about 1 to 2 decs, about a factor of 10 more than what you have in phosphorus normal stars. And these stars here not only have a lot of phosphorus, but also have a kind of chemical abundances in their atmosphere, which is quite abnormal. And you can see this phosphorus, which is very important. You can see a lot of aluminum and silicon. You can see that the iron group are not so much overproduced, but you can see also that you start to have heavy nuclei from strontium, barium, up to europium, and even higher. That these nuclei here, they're not shown as a function of Z, but rather as a function of their symbol, as observed. But these heavy nuclei have been associated with some kind of S-process elements. And as you can see here, it actually, none of the standard thermal nucleosynthesis models have been so far capable of explaining these phosphorus-rich stars. If you take low metallicity, low mass AGB stars, or you take intermediate mass AGB stars, or you take massive stars, or you take type 1a supernova, or you take novae, Masseron and co-workers have shown that actually none of these models do manage to explain first the large amount of phosphorus, but if so, not the amount of the heavier ones, the S-process-like heavy elements. So the question is, again, when nothing works, we can turn to energetic particles, accelerated particles, so-called spallation nucleosynthesis. And we have done the same type of work, trying to see if you take, for example, a carbon target, and you irradiate it with relatively low energies, with alpha particles, in this case, only alpha particles, up to energies of 3 MeV per nucleon, with a given amplitude of the flux. You can see that you start from carbon-12, and as a function of time here, you can see here the irradiation time in seconds and the mass fraction here. You can see that you will transform carbon-12 first in nitrogen-15 by alpha N reaction, or alpha P and so on, alpha N reactions that will make oxygen-15 that will decay into nitrogen-15. And you can see that you will produce little by little other isotopes of nitrogen, carbon, oxygen, but also that little by little, these ones will also recapture these alpha particles. In this specific case, where we don't have an overproduction, very high energies, you will not produce a lot of lithium, barium, and boron, but as soon as you go above, you will. And interestingly, when you see that actually after an irradiation of about 80 years, by a series of alpha captures and also the neutron captures and beta decays that will come out of these alpha captures, you see that you will produce here, as a function of the atomic mass, the overproduction with respect to what you have in the sun. You can overproduce by a factor of 10,000 elements, which are either S-only elements, or S-dominated, or even R-dominated ones. You could actually produce quite a bunch of heavy nuclei through a long irradiation of about 80 years at the specific amplitude for the specific energies. And if we try then to understand the elements of these phosphorus stars, now here shown as a function of the element, the charge of the element, and the overproduction with respect to what you have in the sun at that specific metallicity. You can see for two of these stars, which have been widely studied by Masseron and co-workers last year, if you irradiate it for about 40 years, in this case, 80 years in this case, and then you mix with a given 0.3% or 0.02% this initial material, unaffected material, with this irradiated nuclearly processed material, you find out that is what you would expect as final abundances, which are not perfect, but show that you can get a kind of S process actually just by irradiating by alpha particles this carbon initial material. And you can produce a lot of phosphorus, but some of them are actually not properly always explained, but you could produce quite globally the what you see in these stars. Now to finish, if you irradiate even longer than these years, these 50 or 80 years, and you go up to about 100 years, and you start with material made of carbon, nitrogen, and oxygen, so CNO target, and you irradiate up to 7 MeV, you can see that you start to have not only neutron captures, but also alpha captures on top of it, and you can produce actually molybdenum or ruthenium, as you can see here, in a quite significant amount, overproduction by a factor of 1,000,000 with respect to what you had initially, even the production of lanthanum-138, but this is very speculative, just to show you how, I would say, rich this type of nucleosynthesis could be. And I will finish now. Sorry for having been long. We'll just summarize here that realistic models for thermal nucleosynthesis are more and more available today, though much work is still needed to ascertain some of these astrophysical models. They will remain the main contributors to the galactic enrichments, and it can quite successfully explain most of the observation, though there are still some unexplained and unexplainable observation on top of that. So maybe it's time to revive, as in the 60s, the non-thermal nucleosynthesis, which remain highly speculative. I fully acknowledge that. We have only parametric models today. It's unclear if they would contribute or not to the galactic enrichment, although we know they do for the lithium, barium, and boron. They may explain some very puzzling observation if confirmed, like the chemically peculiar stars, the phosphorus stars, maybe lanthanum-138, maybe molybdenum and ruthenium, but that's even more speculative. But for sure, we would need much more studies, including magnetohydrodynamic effects as we have in this type of environment, stopping power in the astrophysical plasma, all the nucleophysics that is associated. And of course, this could be strongly directed in this direction, oriented in that direction, if we would get from observation the detection of short-lived radioelements like promethium, as I mentioned. And I will stop here, and I will thank you for your attention. And I will just, maybe before we get, I will advise that I take the opportunity to advise that we also have 2 postdoc positions in Brussels for this type of work, both on nuclear theory and astrophysical modeling. And if anybody is interested or has candidates, please do not hesitate to contact me. And I thank you again for your attention.
Thank you very much for this wonderful explanation of this very interesting topic. So the session is now open for questions. Please raise your hand. Virtually, of course. Yeah, I see one question from Projal Banerjee. Please unmute yourself.
Yeah, so I had a question about this spallation, the idea about spallation producing everything up to, heavy elements. So it would seem that if it's such a strong, if it can have such a strong overproduction on the surface, then you probably wouldn't even need, is it possible that you probably don't even need, if you kind of stretch the idea, R process or S process, you can almost get everything from spallation. It seems, and if not, is there a particular kind of stars that are more prone to these, or things like that, right? Because how then would you be confident in seeing some heavy element in a star, Loma star, and then associating it with thermal production versus some non-thermal contribution?
So thermal nucleosynthesis is still there. I mean, I'm not questioning it, and it's still extremely important, and we know it is taking place. Statistically, it is in there, and they will contribute because a lot of material will be enriched by the S process, by the R process, P process, as we know them. Now, we have all around the world, all around the universe, we have these accelerated particles, and the question is, what do? They affect the environment that we know. They heat up the the environment where they are in the jet of supernova, for example, and that can affect in a way or another the nucleosynthesis taking place there. But what if this material is actually interacting on a longer term with the environment, as we do with galactic cosmic rays for lithium, barium, and boron? And in particular, when you look at these AP stars, they are actually, and BP stars, they are actually often related to a strong activity in X-ray emission, which is believed to be linked also to the presence of a strong magnetic field. And so the question is really, to what extent this possibility of having this accelerated particle affecting the material even inside the star. So you can have it somewhere where you have a jet, relativistic jet, that will interact and then pollute interstellar medium that will then later on pollute your star. But you could even have it inside the stellar atmosphere. But now, of course, you have to find out if on the energy balance it makes sense, because you need energy to accelerate these particles, and then you have to take these energies out of somewhere. So all this is very speculative, but it's not. I'm not the first one to mention that. It's been done in the 60s. It's been done on the ideas of promethium, because how can you produce promethium? Okay, you can produce it by fission of transuranium, but up to the point to see it in such a quantity, or that you can identify it in the spectrum, that's something different. So these are really open questions, but for sure, all these studies of chemically peculiar stars have been quite significantly studied by observers, so spectroscopists. And if they come back to this presence of short-lived, like promethium elements in their atmosphere, I think it could open a new field in nuclear astrophysics, about and the impact it has also on the nuclear physics side, because it will require a very different nuclear physics, very different, at least different energy regime of nuclear physics as we do now, as we do study now.
Okay, thanks.
Welcome.
Okay, there is a question by Friedel Tillman.
Hi, thank you for the great talk, Stephane. Just in order to really understand the mechanism of things you have been explaining, you have a very high proton flux and a very high alpha particle flux, and assume that at high energies, and you showed that you could produce very heavy elements, maybe even up to the actinides. I assume you don't do this by proton or alpha capture, but by spallation neutrons. Is that interpretation correct?
Yeah, so the protons and alphas, essentially alpha are much more effective than the protons in that case. So alpha will spallate neutrons, and neutrons will be thermalized, and these neutrons will be recaptured. Now, the typical for the second case that I showed you, so this type of environment here, you typically have neutron densities of the order of 10 to the 10th neutron per cubic centimeters. So you have a kind of S process, and it's now if you push it longer, then you have alpha captures coming in, and this is where you start to see these P nuclei being produced, because then you allow it for much longer time. But before that, now in the first case that I showed you with the Przybylski star, the neutrons were not so efficient because the time scales were much shorter. And then in that case, it's much more by proton and alpha capture that you build up the heavy.
Okay. Thank you.
Any other questions, comments? If not, I might have a very naive one. You were talking about this mixing parameter. So this is fixed completely phenomenologically, or you have some physical basis to introduce this?
No, you can just imagine that the part of the material will be irradiated. Okay.
Yeah.
So this material will then be mixed with material which has not been irradiated, like the atmosphere or the convective envelope of the star. Okay. And you will mix the two. So you cannot say that everything you see at the surface of the star, it has been actually irradiated, but part of it has been irradiated. And then the mixing parameters is indeed the free parameters that you adjust in this case in order to get the overproduction of phosphorus in the star. So it's normalized on phosphorus, if you want. But if you normalize on phosphorus, all the rest of the star of the abundances are fixed, and it's fixed by this red line that you see here. So it's a purely parametric approach in this sense.
Okay. Thank you. I see there is a question in the chat box. So there is a question in the chat box by Carlos Abia. Which is typically the density in your simulations?
So interestingly, the simulations are actually very density independent. So that means if you modify the density by orders of magnitude, you will not change your results. I showed you here some examples of 10 to the minus 7 gram per cubic centimeters. The calculation here with carbon is made with 1 gram per cubic centimeters. And that does not change, because if you decrease the density, you will re-normalize somehow your amount of neutrons, and then you will get the same amount of total amount of neutrons that will be recaptured. So so the density is probably not the most, it's not intuitive. I'm sure it doesn't look like intuitive, but actually it's this set of nuclear reaction network remains relatively insensitive to the density, because if you change the density, you will change the number of neutrons accordingly, actually.
And the overall mass of the star also does not play any role in this whole simulation.
Sorry, say it again.
The mass of the star does not play also any role in this whole simulation.
So we don't consider the mass of the star. You consider some material that is irradiated, and then you mix it. And of course, we have no information on the mass of the material which is irradiated. We have no information about the mass of the unaffected material. We just have these mixing parameters that is linking both. So in that sense, no, we don't have information.
Okay.
And again, we don't know if the irradiation is done, for example, in Przybylski star, if it's done inside the star, in the envelope, which is one possibility. It's a magnetic star with X-ray emitter, it could well be in there, and there are beam calculation trying to find out if promethium could come out of that. Or it is done somewhere totally outside the star, enriching the interstellar medium, and later on the proto-stellar cloud that will make the star.
Okay. Is there any other questions, comments? If not, let's thank Professor Goriely again for this very wonderful, nice talk. And this session will go to Gather Town. For those who did not ask questions here, they might go there and interact with Professor Goriely. So I wish everybody good evening.
Thank you.
Bye.